Digital transmission and pulse code modulation.
Digital transmission. Digital transmission is the transmittal of digital signals between two or more points in a communication system. The signals can be binary or any form of discrete level digital pulses. The original source may be in digital form, or it could be analog signals. A physical facility is required to interconnect the various points within the system. Pulse modulation. Pulse modulation consists essentially of sampling analog information signals and then converting those samples into discrete pulses and transporting the pulses from a source to a destination over a physical transmission medium. Methods of pulse code modulation include PWM, PPM, PAM, and PCM. We'll discuss each one. Pulse width modulation. Pulse width modulation, also called pulse duration modulation or pulse length modulation. The width of a constant amplitude pulse is varied proportional to amplitude of the analog signal at the time the signal is sampled. The maximum analog signal amplitude produces the widest pulse, and the minimum analog signal amplitude produces the narrowest pulse. This is an example of a pulse width modulated signal. As you can see, in the first waveform, we have a regular sine wave. The second waveform is the sample pulse. As you can see, they are continuous, constant amplitude, and constant frequency pulses. And then the result, we have the last waveform. This is the pulse width modulated signal. The width of each pulse is directly proportional to the amplitude of the sine wave being sampled at that moment. Pulse position modulation. The position of a constant width pulse within a prescribed time slot is varied according to the amplitude of the sample of the analog signal. The highest amplitude sample produces a pulse to the far right, and the lowest amplitude sample produces a pulse to the far left. Now, let's take a look at an example for pulse position modulation. Again, for the original message signal, we'll have a regular sine wave. And then, for the sample pulse, we still have the constant amplitude, constant frequency pulses. And then lastly, this is the pulse position modulated signal. As you can see, the position of the pulse is directly proportional to the amplitude of the original signal. The higher the amplitude, the farther to the right the pulse will be, and the lower the amplitude, the farther to the left the pulse is. Pulse amplitude modulation. The amplitude of the constant width, constant position is varied according to the amplitude of the sample of the analog signal. The amplitude of a pulse coincides with the amplitude of the analog signal. The waveforms resemble the original analog signal more than the waveforms of PWM or PPM. Again, let's take a look at another example. For pulse amplitude modulation, we still have a regular sine wave as our analog signal, and then the sample pulses, and then we have our pulse amplitude modulated signal. As you can see, the amplitude of the pulses for the modulated signal is directly proportional to the amplitude of the original analog signal. Pulse code modulation. The analog signal is sampled and then converted to a serial n-bit binary code for transmission. Each code has the same number of bits and requires the same length of time for transmission. Pulse code modulation. Alex H. Reeves invented PCM in 1937 while working at AT&T at its Paris laboratories. In the US, it is the preferred method of communications within the public switch telephone network, since it is easy to combine digitized voice and digital data into a single high-speed digital signal and propagate it over the either metallic or optical fiber cables. Pulse code modulation is the only digitally encoded modulation technique which is commonly used for digital transmission. The pulses used are of fixed length and fixed amplitude. A binary system where a pulse or lack of a pulse within a prescribed time slot represents either a logic 1 or a logic 0 condition. Now let's take a look at an example of a PCM waveform. Again, we have our analog signal, which is a continuous sine wave. Next, we have our constant amplitude, constant frequency sample pulses. A pulse code modulated signal is generated. Basically, it consists of 8 bits per word or per sample, and the number and positions of bits that are at a high level, meaning that the amplitude is not 0 or it is a logic high, is dependent upon the amplitude of the original analog signal. As you can see, different amplitudes would produce different 8-bit words. PCM transmitter. This is a block diagram of a simple PCM transmitter. First, we have our input signal, which is an analog signal. It will pass through a bandpass filter. The bandpass filter limits the frequency of the analog input signal. For example, if we want the standard voice band frequencies, it will filter the signal to only allow a frequency range of 300 Hz to 3000 Hz. And then after passing through a bandpass filter, it will go to the sample and hold circuit. The sample and hold circuit is basically the counterpart of a modulator for an analog modulated signal. What the sample and hold circuit does is it periodically samples the analog input signal and converts those samples to a multi-level pulse amplitude modulated signal, or PAM. The PAM signal would then go to the analog to digital converter, or ADC, that converts the PAM signals to parallel PCM codes, which are converted to a serial binary data in the parallel to serial converter. It will then be sent onto our transmission line, which is our medium. The regenerative repeaters are placed at prescribed distances to regenerate the digital pulses. In the receiver, the serial to parallel converter converts serial pulses received from the transmission line to parallel PCM codes. The digital to analog converter, or DAC, converts the parallel PCM codes to multi-level pulse amplitude modulated signals. The hold circuit is basically a low-pass filter that converts the PAM signals back to its original analog form. Sampling. The function of the sampling circuit is to periodically sample the continually changing analog input voltage and convert those samples to a series of constant amplitude pulses that can be more easily converted to binary PCM codes. Two basic techniques: natural sampling and flat top sampling. Natural sampling. In natural sampling, the tops of the sample pulses retain their natural shape during the sample interval, making it difficult for an ADC to convert the sample to a PCM code. The frequency spectrum of the sampled output is different from that of an ideal sample. Let's take a look at an example of the natural sampling. First, we have our input waveform, which is just a basic sine wave, and then our sample pulses of constant amplitude and constant frequency. The output waveform, this is what we call a naturally sampled signal. So as you can see, it consists of various pulses, which is aligned to our sample pulse. But the amplitude of these pulses are directly proportional to our input waveform. And the top of these pulses are not constant in amplitude. Next, we have the flat top sampling. This is the most common method used for sampling voice signals in PCM, which is accomplished in a sample and hold circuit. Its purpose is to periodically sample the continually changing analog input voltage and convert those samples to a series of constant amplitude PAM voltage levels. The input voltage is sampled with a narrow pulse, then held relatively constant until the next sample is taken. This is an example of a flat top sampled signal. First, we have our input waveform, which is just a basic sine wave. Next, we have our sample pulse, which are pulses of constant amplitude and constant frequency. It will then result in the output waveform seen below, which is a flat top sampled signal. As you can see, the amplitude of these pulses are directly proportional to the amplitude of our input waveform. The only difference of this and the natural sampling is that the amplitude of every pulse in the output waveform is constant. This is a simple sample and hold circuit. Let's take a look at the circuit. First, we have our analog input signal, which is just a basic sine wave. It will pass through a buffer, and then we have Q1, which is any kind of a FET. Basically, what the Q1 does is when there is an input pulse in its gate, the drain to source will essentially be a short circuit. And when the pulse is in the 0 volts, the drain to source will essentially be an open circuit. Now, during the pulse, the capacitor charges so as to maintain the voltage level of the input analog signal. And then it will pass through another buffer amplifier, and the output would be a pulse amplitude modulated signal with a flat top sampling. Now let's take a look at the waveforms below to understand how the PAM is generated. First, the input waveform, just a basic sine wave, and then there are sample pulses. We have two examples of sample pulses, one in a high level and another during the low level of the input waveform. So first, during the input pulse, the capacitor charges. As you can see in the third waveform, the capacitor charges to match the amplitude of the original waveform. After the pulse, we have a few nanoseconds or microseconds of off time. So there will be a slight droop as the capacitor loses some of its charge. It's just a little value, so it will just be a little droop. Ideally, there will be no droop, but in reality, the capacitor will lose some of its charge. So then during the next pulse is situated during a low voltage level of the input waveform. So the capacitor discharges to match the amplitude of the original waveform. Of course, these sample pulses are spaced farther apart just for the sake of this example, but in reality, the sample pulses would be closer together so that the input waveform will be remodeled as close as possible in the PAM output signal. Sampling rate. The Nyquist sampling theorem establishes the minimum sampling rate, F sub s, that can be used for a given PCM system. The minimum sampling rate is equal to twice the highest analog input frequency. To put it into a formula, F sub s is greater than or equal to 2 times F sub a, where F sub s is the minimum Nyquist sampling rate in Hertz, and F sub a is the maximum analog input frequency, also in Hertz. Aliasing. If F sub s is less than 2 times the F sub a, this is a condition known as aliasing. It is also called a foldover distortion. Let's take a look at a sample problem for Nyquist rate. For a PCM system with a maximum audio frequency of 4 kHz, determine the minimum Nyquist sample rate and the alias frequency produced if a 5 kHz signal were allowed to enter the sample and hold circuit. So first question, let's determine the minimum Nyquist sample rate if the maximum audio input frequency is 4 kHz. So to get that, we just have to multiply 2 times the maximum audio input frequency, which is 4. So let's write that down. F sub s is equal to 2 times 4 kHz. And then it will be equal to 8 kHz, just simple multiplication. So the minimum Nyquist sampling rate for a maximum audio input of 4 kHz is 8 kHz. Next, we have to find the alias frequency produced if a 5 kHz audio signal were allowed to enter the sample and hold circuit. Now, to get this alias frequency, we just have to subtract the Nyquist sampling rate, 8 kHz, minus the frequency at which the audio signal is above the maximum audio input frequency. In this case, it's 8 kHz minus 5 kHz. So we have 3 kHz. And as you can see in the image below, alias frequency is at 3 kHz, meaning that another frequency would be generated due to aliasing. Pulse code modulation. The analog input signal is sampled, then converted to a serial binary code. The binary code is transmitted to the receiver, where it is converted back to the original signal. The binary codes used for PCM are n-bit codes, where n may be a positive integer greater than 1. The codes currently used for PCM are sign magnitude codes, where the MSB is the sign bit and the remaining bits are used for magnitude. The MSB is used to represent the signal of the sample. MSB is short for most significant bit. The other bits represent the magnitude. N-bit PCM code, wherein n is equal to 3. As you can see, there are 3 bits in this example. We have the sign bit, and we have the magnitude. The sign bit consists of only 1 bit. The magnitude consists of the 2 other bits. And then lastly, we have the decimal value. So meaning for each combination of the PCM code, there is a corresponding decimal value. For a sign bit of 1 and a magnitude of 1, 1, we have positive 3. And then for a sign bit of 1 and a magnitude of 1, 0, we have the decimal value positive 2. And so on. The sign 1 denotes positive, the sign 0 denotes negative. Quantization. The process of converting an infinite number of possibilities to a finite number of conditions. It is the process of rounding off the amplitudes of the flat top samples to a manageable number of levels. The voltage range is subdivided into a smaller number of sub-ranges. Quantization interval, or quantum. This is the magnitude difference between adjacent steps. Overload distortion, or peak limiting. This is the magnitude of the sample exceeds the highest quantization interval. Resolution. Resolution is the magnitude of the quantum. This is equal to the voltage of the minimum step size. 3-bit PCM code. So this is again, n is equal to 3. There are 8 sub-ranges. Still, there is 1 sign bit and 2 magnitude bits. The decimal value is still positive 3 up to negative 3. As you can see here, there is an added column, quantization range. The quantization range gives us the range of values for which the sampled flat top signal will be approximated to a specific decimal value. For example, for a quantization range of 2.5 volts to 3.5 volts, it will be approximated to a decimal value of positive 3 volts. Similarly, when the flat top amplitude is between 1.5 volts to 2.5 volts, it will be approximated to a value of positive 2 volts. Analog signal to PCM code. In this image, we have 4 kinds of signal. In the first, we have our analog input signal, which is a continuous signal of varying amplitude. And then we have our sample pulses, our constant amplitude, constant frequency pulses. And then we have the pulse amplitude modulated signal. As you can see, this is a flat top PAM signal. So every amplitude for this PAM signal has a corresponding voltage level. And every corresponding voltage level has a specific combination of bits. For positive 3, it is 111. And for the first pulse, it is approximately equal to positive 2 volts, meaning that the equivalent PCM code for this is 110. That is why 110 is indicated below the first pulse. The second pulse, it's approximately equal to negative 1 volt. Negative 1 volt, when encoded, is equal to 001. So 001 is the code below negative 1 volt, and so on. Now, for a 2.6 volt amplitude, the quantized voltage would be equal to 3 volts. Because as we have seen earlier, the range between 2.5 volts to 3.5 volts would be approximated to positive 3 volts. So the quantized voltage is positive 3 volts, and the quantization error, meaning that the error of the approximated value versus the original value, is positive 3 volts minus positive 2.6 volts is 0.4 volts. So the quantization error is 0.4 volts. And then lastly, the encoded bit for positive 3 volts is 111. That is why 111 is written underneath the positive 3 volts amplitude signal. Quantization error. Quantization error is also called quantization noise. This is an error equivalent to additive noise as it alters the signal amplitude. Any round of errors in the transmitted signal are reproduced when the code is converted back to the analog in the receiver. Now, sampling at a higher rate will produce a pulse amplitude modulated signal that is closer to our original analog signal than when the samples are at a lower frequency. Example, for the PCM coding scheme shown in the example, let's take a look at an example problem. For the PCM coding scheme shown in the example, determine the quantized voltage, quantization error, and PCM code for the analog sample voltage of 1.07 volts. This is just like the example earlier. So for a sample voltage 1.07 divided by the resolution 1, we have 1.07. And since there is no PCM code for positive 1.07, therefore the magnitude of the sample is rounded off to the nearest valid code, which is 101, or positive 1 volt. So we have our quantized voltage, positive 1 volt, our PCM code is 101, and the rounding off process results in a quantization error of 0.4 volts. That's it, very easy. Next, dynamic range. Dynamic range is the ratio of the largest possible magnitude to the smallest possible magnitude, other than 0 volts. That can be decoded by the digital to the analog converter in the receiver. The formula is dynamic range is equal to Vmax, which is the maximum voltage magnitude that can be discerned by the digital to analog converters in the receiver, divided by Vmin, which is the quantum value or resolution. Dynamic range is a unitless quantity. The number of bits used in a PCM depends on the dynamic range. The formula for this is 2 raised to n minus 1 must be greater than or equal to dynamic range. So the minimum number of bits is just 2 raised to n equals dr, or dynamic range, plus 1. So you just have to solve for n. And then the dynamic range can also be expressed in decibels. The formula is 20 log 2 raised to n minus 1. Dynamic range versus number of PCM bits required. As you can see in this table, as the number of bits in PCM code increases, the number of levels possible also increases, and the dynamic range, expressed in decibels, would also increase.
Coding efficiency. Coding efficiency is a numerical indication of how efficiently a PCM code is utilized. It is the ratio of the minimum number of bits required to achieve a certain dynamic range to the actual number of PCM bits used. Coding efficiency is equal to the minimum number of bits, including signed bits, divided by the actual number of bits, also including signed bits, times 100%.
Example: for a PCM system with the following parameters, determine A. Minimum sample rate, B. Minimum number of bits used in PCM code, C. Resolution, and D. Quantization error.
First, let's find the Nyquist rate. Nyquist rate is quite easy. It's just 2 times the maximum analog input frequency. So 2 times 4 kilohertz, and we have 8 kilohertz. It is the Nyquist rate. Next, let's find the minimum number of bits if PCM is used. So from the dynamic range of 46 decibels, we can compute n, or the minimum number of bits. So let's use the formula. Dynamic range in decibel is equal to 20 log of 2 raised to n minus 1. So simplifying the equation, we have 46 divided by 20 equals 2 raised to n minus 1. And further simplification would produce n equals 7.64. Now we cannot use 7.64 number of bits, so we have to round that up to n equals 8. We can see here that 8 bits must be used for the magnitude, but one additional sign bit is required to indicate positive and negative voltage levels. Thus, the minimum number of bits is 9. So answer to letter B is 9. Next, let's find the resolution. We have a formula for this. Dynamic range equals Vmax over Vmin. Vmin is our resolution. So let's just manipulate the equation. We have resolution equals Vmax over dynamic range. So Vmax is given 2.55 volts divided by 2 raised to n minus 1, our dynamic range. And for the value of n, we're going to use 8, just considering the magnitude. Next, we have to find the quantization error. This is just the resolution divided by 2. So we have 0.01 divided by 2 equals 0.005 volts. And lastly, the coding efficiency. We have a formula for this. It's the minimum number of bits, including the sign bit, divided by the actual number of bits, also including the sign bit, times 100%. As for why 8.64 is used here, remember our answer in letter B. We actually got n equals 7.64, but we must include the sign bit, so plus 1. 7.64 plus 1 equals 8.64. That's why 8.64 is used as the minimum number of bits, including the sign bit. Signal to quantization noise ratio. Worst case occurs when the input signal is at minimum amplitude. Worst case voltage SQR is SQR equals resolution over the quantization error, or Q sub E. SQR for maximum input signal is SQR sub max equals voltage maximum divided by the quantization error. Vocoders. These are encoder or decoders used to digitize speech signals only. It is actually short for voice encoder or voice decoder. Its purpose is to encode the minimum amount of speech information necessary to produce a susceptible message with fewer bits than those needed by a conventional encoder or decoder. This is used primarily in limited bandwidth applications. There are three vocoding techniques: 1. Channel vocoder, 2. Format decoder, and 3. Linear predictive coder. First, channel vocoder. The first channel vocoder was developed by Homer Dudley in 1928. It compressed the conventional speech waveforms into an analog signal with a total bandwidth of approximately 300 Hz. The present-day digital vocoders operate at less than 2 kbps and use bandpass filters to separate the speech waveform into narrower subbands. Format vocoder. Format vocoder takes advantage of the fact that short-term spectral density of typical speech signal seldom distributes uniformly across the entire voice band spectrum, which is 300 Hz to 3 kHz. It simply determines the location of the peaks and encodes and transmits only the information with the most significant short-term components. Lastly, we have the linear predictive coder. Linear predictive coder extracts the most significant portions of speech information directly from the time waveform rather than from the frequency spectrum, as with the channel and format decoders. It produces a time-varying model of the vocal tract excitation and transfer function directly from the speech waveform. It typically encodes and transmits speech between 1.2 kilobits per second and 2.4 kilobits per second. PCM line speed. PCM line speed is simply the data rate at which serial PCM bits are clocked out of the PCM encoder onto the transmission line. It is dependent on the sample rate and the number of bits in the compressed PCM code. The formula is line speed equals samples per second multiplied by bits per sample. So in this formula, sample would cancel out, leaving the unit of line speed as bits per second. Let's take a look at an example. For a single channel PCM system with a sample rate of 6,000 samples per second and a 7-bit compressed PCM code, determine the line speed. This given 7-bit compressed PCM code is already our bits per sample. So we directly multiply the given 6,000 times 7 and we have 42,000 bits per second, or 42 kilobits per second. Delta modulation PCM. Delta modulation PCM uses a single bit PCM code to achieve digital transmission of analog signals. Rather than transmit a coded representation of the sample, only a single bit is transmitted, which simply indicates whether that sample is larger or smaller than the previous sample. If the current sample is smaller than the previous sample, a logic 0 is transmitted. If the current sample is larger than the previous, a logic 1 is transmitted. Delta modulation transmitter. The input analog is sampled and converted to a pulse amplitude modulated signal, which is compared with the output of the digital to analog converter. The output of the digital to analog converter is a voltage equal to the regenerated magnitude of the previous sample, which was stored in the up-down counter as a binary number. The up-down counter is incremented or decremented depending on whether the previous sample is larger or smaller than the current sample. Now, this will be the ideal operation of delta modulation encoder. As you can see, the analog signal is a continuous, time-varying signal, and when the next step is higher in amplitude than the previous step, the PCM code is 1. Conversely, if the next step is lower in magnitude than the last step, then the PCM code is 0. Delta modulation. Each sample requires the transmission of only one bit. Therefore, the bit rates associated with delta modulation are lower than conventional PCM systems. There are two problems associated with delta modulation that do not occur with conventional PCM. First is the slope overload, and second is the granular noise. Slope overload. Slope overload occurs when the analog signal changes at a faster rate than the DAC can maintain. The slope of the analog signal is greater than the delta modulator can maintain. Increasing the clock frequency reduces the probability of slope overload occurring. Another way to prevent slope overload is to increase the magnitude of the minimum step size. This is more prevalent in analog signals that have steep slopes or whose amplitudes vary rapidly. This is an image of slope overload occurring. As you can see, our analog input signal has a very steep slope. So this rapid change in amplitude is too fast for our system to follow. So our DAC output is lagging behind our original analog input signal. Granular noise. This is the other problem with delta modulation. Granular noise is analogous to quantization noise in PCM. It is when the original analog input signal has relatively constant amplitude, the reconstructed signal has variations that were not present in the original signal. This can be reduced by decreasing the step size. More prevalent in analog signals that have gradual slopes and whose amplitudes vary only small amounts. This is an example of the occurrence of granular noise. As you can see, our original signal looks just like an arc, but when delta modulation sampled the signal, the resulting output is a changing PAM waveform. So when it is reconstructed, there are variations in the amplitude that doesn't quite match the original signal. Adaptive delta modulation. This is a delta modulation system where the step size of the DAC is automatically varied depending on the amplitude characteristics of the analog input signal. This is an example of an adaptive delta modulation signal. As you can see in the early part, our PAM is lagging behind the original analog signal. So what the adaptive delta modulation does is it increases the step size when it detects a continuous bit of ones. If you can remember, delta modulation produces a bit of 1 if the next step is higher in amplitude than the previous step. So continuous bits of 1 means that there is a slope overload occurring. So when it increases its step size, it lessens the probability of slope overload. And then again, on the second part, we can see slope overload occurring again, but this time it detects a continuous string of zeros because the next step is lower in amplitude than the previous step. So again, what the adaptive delta modulation does is when it detects a continuous string of zeros, it increases the step size downwards. So as you can see, slope overload is also reduced. And then for the granular noise to be minimized, When the adaptive delta modulation detects a continuous string of alternating ones and zeros, it means that there is a high probability that granular noise is occurring, and so it lessens the step size as to minimize the granular noise. And that's it.